Okay. So with the fundamentals in place now, we can consider the instrument a little bit. So we saw we were going to take a radiation source, a wide beam of all the same wavelength of the incident X-rays is going to be imposed onto the sample. The sample will have a surface which helps us establish the angle of incidence, also called the Bragg angle, theta. And we might expect that if the sample plane was continued and the beam was allowed to pass right through the sample, the path of incidence is here. And so we have, of course, this angle here as our incident angle, theta, again. Okay, and so the architecture of instruments is often to place a detector for monitoring for constructive and destructive interference as beams are reflected out of the sample, is to position that at the same angle, at the Bragg angle. So here you see the detector from the plane of the sample, it has been moved to an angle theta up away from the plane of the surface. Okay, and so for historical reasons, the graphing that results, the data that results from X-ray diffraction, is actually defined as an x-axis that is the 2 theta. So it's the angle between the incident beam path swept all the way through to where the detector is. And that represents the x-axis coordinates for our information. Okay, so shown a little bit better here is that as we try to sweep and acquire data, that we're expecting the x-axis of our graph to be 2 theta as we consider moving the detector through a range of 2 theta values for the sample. Okay, so the detector will sweep angles as at a rate that matches the X-ray source sweeping in the opposite direction. Okay, and then our collectors, of course, monitoring the intensity of detected X-ray intensity, and that might give us peaks and low intensity and peaks, provided that we satisfy Bragg's law. Okay, so in other words, here's how the process might go. We'll collect a set of intensities, so we'll monitor data, and until there's Bragg's law satisfied, there'll be no intensity of detected light at a certain 2 theta value, again, where the incident beam would be relative to where the detector is. Okay, so 2 theta is here. And once Bragg's law is satisfied, then we'll build intensity at the detector, and then as Bragg's law is unsatisfied, then we'll return to almost baseline intensity, very little just background intensity at the detector. And then once Bragg's law is satisfied again, perhaps we'll get another peak of intensity in our X-ray diffractometer. So here we have the position 2 theta generated by the mechanics of moving the X-ray source and the detector sweeping towards each other through lots of options for 2 theta, and then monitoring the amount of intensity for the X-rays at that detector. Okay, and then through either tabulated information and what's known for certain materials, we could identify planes detected, so identify the D values from Bragg's law ultimately by solving for Bragg's law, solving for D, and then deducing what planes must be responsible, and we'll see that in a moment. Okay, so here's another data set just to sort of enlarge things. This is the data set for powdered aluminum Here you can see we're specifying now what incident radiation was imposed onto the powdered aluminum. So it was a lambda of X-rays corresponding to wavelength 0.1542 nanometers, so very small wavelengths on the order of the distance between atoms. And here we see the various planes that are responsible for satisfying Bragg's law and allowing us to detect diffracted X-rays at the detector. Okay. Good. So some other kind of requirements for Bragg's law. So again, Bragg's law was n lambda is equal to 2d sine theta. And some other requirements for parallel planes of atoms with a spacing that is the same of h, k, and l between those planes, we want to see destructive interference when we satisfy the equation above, Bragg's law. In most diffractometers, the incident radiation is fixed. So in the previous example, we saw copper K alpha, which was equal to 0.1542 nanometers there. So that is a constant. So far, the left-hand side is looking constant. As we know, crystals are often very large and include very many sets of unit cells, and so we would expect many planes of atoms next to each other. And so we have families of planes that may diffract only at a very specific angle, theta. A requirement for the geometry of the conditions for incident radiation and where the detector is in our sample is important here. So the plane normal must be parallel to the diffraction vector. Okay. So a diffraction vector here is defined by the following. So a plane normal is the direction perpendicular to the plane of atoms. So here in the diagram above, that would be the dotted line. That is our plane normal. And now, what is the diffraction vector? The diffraction vector is the vector that bisects the angle between the incident and diffracted beam. Okay, so that's also right there. Okay, so those two must be parallel, of course. If they're not, if the angle of incidence and our lattice was not as shown, but on angle. So I'll try to draw those black lines here now like this. You can see that the plane normal is not parallel to the diffraction vector. And so those are no longer parallel, and we would not satisfy the condition of our instrument and allow for detection at our detector. Okay, so hopefully that clarifies it. So clearly something important about how the planes are oriented relative to the sample. Okay, just clean that up so we can see the corrected version there. Okay. And as we've seen before, just to reemphasize, the spacing between diffraction planes helps us determine where the peaks would be located in our XRD graph. And the peak intensities are a consequence of several things. We would expect at the very least what atoms are present in the sample. So if we have very large atoms packed very closely, we're going to be very efficient at scattering X-rays towards the detector. If the atoms are very small and far away, we might expect just a lower intensity at the detector, even when Bragg's law is satisfied. Okay. So to emphasize that earlier point about the plane normal being off angle from the diffraction vector, we show that here. So in the case where a single perfect crystal, in this case a garnet ruby, is studied, we have perfect planes of atoms all the way through this crystal, all the way through. It's a perfect crystal. And so in the case of the 100 plane and the family of those, we would satisfy this requirement for the diffraction angle being parallel to the diffraction vector being parallel to the plane normal, and so we would expect intensity there. Bragg's law would tell you that you should find an intensity here at around 29.5 degrees 2 theta, but because our plane normal is off angle from our diffraction vector, which bisects the angle of incidence from that where we have our detector, that we will not see the predicted 110 because the sample planes are not aligned correctly. So if we could rotate those somehow, then the 1110 would grow in. Likewise, for the 111 and the 200 is also now satisfying Bragg's law, and the diffraction vector is parallel to that of the diffraction vector. The plane normal and the diffraction vector are parallel. To solve this problem, engineers and scientists will often granulate their sample, make a powder out of it. This helps create a layered material full of many tiny crystals that are randomly scattered throughout all options in their orientation in the layer of sample, as you sort of see depicted here. So this could be the same sample just ground up, made into a powder. And this allows us to reposition random pieces of crystals throughout the sample. This would allow families of planes, like that represented here by the 110, to now have their plane normal parallel to the diffraction vector. And now this satisfies the requirement for detecting those Bragg's law predicted intensities, in this case at the 110, and we also see the 111 present as well. Okay, so powdered samples give more information in X-ray diffraction. Okay. We mentioned briefly that the sets of atoms is responsible for how high these peaks are. And the next piece we'll consider here is that the peak intensity is also related to how many planes we have available to help us with the diffraction. So in other words, how big are these crystals? If that red crystal there is very large, we have many sets of planes. And so the crystal size being very large helps us have enough sets of planes to build intensity at the detector. But if it's very, very small, only a few sets of planes, we don't have enough density of planes of atoms to build us intensity at the detector. So the peak intensity is not only related to the type of atoms involved, but it's also related to the extent of crystallinity of a particular plane. Okay? So how far sets of planes, for example, if we could extend the lattice, which we know is represented by the unit cell, and we could extend this very, very far, the set of 200 planes here would be very deep into the sample, and we'd expect large intensities here. If the sample was very short, we didn't have a lot of crystallite present, that is this dimension before we go to a different orientation, a different crystal with a different orientation, or to a boundary of the material, then the intensity is going to drop.